Hello all, welcome back. In all our previous tutorial we have used either Vivado for implementing some custom circuits on the PL part of Zinc, or we use the SDK to implement some software on the PS part of Zinc. So in this project we are going to use both the processor part as well as the PL part, and we will see how these two parts can communicate with each other. So we are attempting a very simple design. So what we are trying to do is we will have a circuit in the PL part which will control the LED, and the processor will be writing to this custom hardware, and based on what value the processor writes to this circuit, the corresponding LEDs will turn on. Okay, so this is like the hello world program for hardware software Codesign. You can think like that. So in order to do this, we'll be using the IP tool flow of Vivado. Till this point, we haven't used any IP. We were writing all our code in Verilog directly, but in this project, we'll be using IPs, and you'll see how they look like. So I'm starting as a new project again, and let me call it hardware software hello world or something. Okay, so in order to use the IP flow, you should go to this option, create block design, under IP integrator. Okay, so you just go and click there, and you're basically going to draw a block design actually. So we need to give some name to the design. So let's call it something like LED control or something. You can give whatever name you like, and you will get this screen, which will be used for integrating the IPs. So as we discussed before, IPs are intellectual properties. So these are basically, they will look like blocks here, some pictorial representation, but actually there are Verilog codes associated with each of this IP. Okay, so you can design a circuit simply by dragging and connecting IPs together, and when you implement your circuit, implement your design, Vivado will fetch the corresponding Verilog code or VHDL code for each of these IP, and he will actually implement it. Okay, that's what is going to happen. Now, if you want to use the PS in your design, in your IP based flow, the first IP that you should add is the Zinc PS. So you click on this button, add IP here, or on this button, and it will list a lot of IPs. Okay, so all these IPs come with Vivado by default. In addition to these IPs, you can buy IPs from third parties, or you can develop your own IPs also. Okay, so see, this IP is for controlling Ethernet. We have very simple IPs like accumulator for adder subtractor. Lot of IPs are there. So one IP that you will always use if you want to use the PS is Zinc processing system. So just type Zinc here, he will list this one, Zinc processing system. Okay. Yeah, so as I mentioned before, you will see all the IPs as some blocks here. Now this is the PS part of Zinc, and if you remember, PS, it has four AXI interfaces to the PL part. We call it GP ports, as well as it has high performance AXI interface to the PL part, which we call as the HP port. Now when you add it here, by default you will see something called MAXI GP0 here. Okay, so this is the AXI GP port, one of them. Now if you want to have more than one GP, or if you want to make any change to the processing system, you double click it, and you can see the entire architecture of our PS, and you can selectively enable or disable different parts of it. For example, if I go here, 32-bit GPXE master port, if I double click here, you'll see like MXEGP0 is checked. Okay, so that's why you are seeing MXEGP0 here. If you check this option also, MXEGP1, and click OK, you will see MXEGP1 also. Okay, so these are the two XE general purpose ports which will be used for connecting with the peripherals that you will implement in the PL part of the Zinc chip. Okay, so let me go back and make it only GP0, because for this project we need only one XE interface. Now once you add this, you will automatically see this option here, run block automation. You click this and click OK. So what is going to happen is the DDR interface, this one, as well as so-called fixed IO. So these interfaces include UART, SPI, I2C. So all these interfaces that you are seeing here on the left, SPI, I2C, CAN, UART, all these interfaces will be automatically constrained. The pin constraint for all these interfaces is automatically done by Vivado, because he knows you are using Z-board and where the DDR is connected or where the USB is connected, etc. Okay, so only if you choose Z-board at the beginning, he'll be able to automatically do it for you. Fine. Now next one, we are going to control our LEDs. Okay, the IP which can be used for that purpose is called GPIO IP. So I again click add IP and choose XE GPIO. So GPIO stands for general purpose input output. Okay, so if you want to control some LED, you want to read from some switches, for all those purposes, this is the best IP code to use. Now one thing you may want to do is you want to know how to use this IP and other details about the IP. So you may want to see the documentation for this IP, the user guide. So actually you can right click and there is an option here, IP documentation, and you can choose view product guide, and Vivado will open the user manual for you, and there you can go ahead and read all the details for this IP. Okay, so that's how we usually learn about the IP. Now once you add this IP here, you need to connect the PS with this IP. Okay, so PS is a hard IP core. This is a fixed IP inside the chip. This IP, XCGPIO, is a soft IP, and this will be implemented in the PL part of the Zinc chip. And how do you connect these two things together? You connect them using the XE interface. So if you see here, there is a XE interface and there's a prefix M, which stands for master, and here there is an XE interface with prefix S, which stands for slave. Okay, so Zinc is the master. He is the one who initiates all the read and write operation, and XGPIO, he's a slave. Okay, so he just responds to whatever read and write operations are initiated by the master. Now you need to connect them together. Okay, now one easiest way to connect them together is you will automatically have this option here, run connection automation. You click it and you choose all the interface. Before that, we need to do a customization for this GPIO. So you double click it. Any IP, if you want to do customization, you just double click it and this IP customization will come, and there you can choose some option. So actually this GPIO IP, it has two interfaces. It can control actually two things. It can control LEDs, it can control switches, or it can control LED as well as switches. Okay, now by default he will show only one GPIO here, but if you come here IP configuration and click on this option enable dual channel, he will show both the GPIO and GPIO2. Okay, so these are the two GPIO. Now my plan is only to control the LED, so I'm just disabling the second channel. Now here again under GPIO, where this IP should be connected in the external world. Okay, now if your plan is to control the LED, you can click this option and choose LEDs 8-bit. Now what is going to happen is, again, Vivado, he knows you are going to use Z board, and this will be implemented in Z board, and he automatically knows the pin constraints for the LEDs on Z board. Okay, so if you choose LEDs 8-bit here, you don't have to do pin constraints for LED in this case. Similarly, GPIO2, if you choose switches 8-bit, okay, GPIO2 comes and he'll automatically do the pin constraint for slide switches. Let me again disable it. Okay, now let's click run connection automation and you choose all automation and click OK, and you'll see a lot of things actually happens. Okay, now you can click on this button here, regenerate layout, so that he will nicely arrange everything. So let's see what actually happened. So we have the Zinc processing system here, and this is the XE master port. From there he took a connection and connected to another IP called XE interconnect, and from XE interconnect he actually connected to the GPIO, and the output of GPIO is connected to some pin. Okay, so this symbol indicates these pins, actually this arrow kind of thing, they are connected outside the chip. That is the meaning. Now you will also, another interesting thing is, in all our previous designs we were taking the clock signal from Y9 pin of the board. Okay, because you had only custom hardware in your PL and it was working independent of the processor. In this design that is not the case. You have processor, you have peripheral, and all of them should work synchronously. So the clock signal for all the peripherals in your design will be provided by the PS, the processing system. So you'll see a signal here, FCLK clock 0, and this is the output from that, and you will see that signal is actually connected to the clock signal of the GPIO. Okay, so that again Vivado automatically does it for you. You don't have to do any clock constraint here because the clock is not coming from external pin, and you also don't have to specify what is the clock frequency, because if I again double click and look at the clock here under clock configuration, you will see PL fabric clock, and this option is checked, FCLK clock 0, and it is going to run at 100 megahertz. Now if you want to increase the frequency for better performance, you can just go ahead and change this value to 150 or 200, up to 250. Okay, now the processor actually can give 4 independent clocks also if your design requires that, and these 4 clocks can be running at 4 different frequencies, but for our current design only 1 clock is enough, so we keep it at 100 megahertz. So again, you don't have to specify any clock frequency constraint because he automatically already knows like this clock is running at 100 megahertz. It is not coming from the crystal. Fine. Now how the processor will interact with GPIO. So for this we need to remember a few points from our computer architecture course. Okay, from the processor point of view, every peripheral in the system is just like a memory. Okay, that is what is happening from the processor point of view. So next to this diagram tab you will see something called this address editor, and if you go there you will see XGPIO0, which is the instance name of this IP, XGPIO0, and there it is written offset address 4120.0000, range 64K, high address 4120FFFF. What this basically means is whenever the processor reads or writes, okay, in this address range, that read and write operation will happen from this GPIO. So if you have many peripherals in your system, each of them will have a unique address range, and any read and write from a particular address range will happen from that particular peripheral. So from processor point of view, everything looks like a memory, but physically they need not be memory. This he feels like it's a memory, but here it's not a memory. Here it is a GPIO IP core, which is not a memory, but he feels like he's reading and writing from a memory, but effectively he's reading and writing from this IP core. And that is where this XE interconnect also comes into picture. So you'll see like this GP0 is connected to this interconnect. Now what the interconnect does is, maybe to show this, I will add one more IP core. Okay, run connection automation. Okay, I have added one more GPIO just as a dummy purpose, just to show you what this interconnect actually does. Now if you see the interconnect, it is actually connected to the processor MXGP0, and it is connected to these two IP. And now if I come to the address editor, I will see two address ranges. Okay, this is for first GPIO, this is for the second GPIO, and there is no overlap between them. Now if I read or write from this address range, it should go to GPIO 0. If I read or write from this address range from the processor, it should go to the second GPIO. Now what this interconnect does is, whenever the processor reads or write, okay, he checks the address within which he is reading and writing, and based on whether that address range belongs to this GPIO or whether that address range belongs to this GPIO IP, he will send that transaction to the appropriate IP. So you can think like this is more or less like a demultiplexer. He gets some transaction from the processor, he checks the address of the transaction. Based on the address, he routes the transaction to the appropriate peripheral. That is what the interconnect does. Okay, so let me delete it again. And okay, I don't want this second interface, so I can just double click and say number of masked interfaces back to 1. Okay. Okay. No. Okay, so for our, and let's delete this one also. And for our current project, this much is enough. One thing you need to do is, once you create block design, save it, and you click on this button, validate design, and Vivada will check your block design. If there is anything wrong, he will tell you so and so things are wrong, so you need to correct those errors. Usual errors are the clock signals you forget to connect, or the reset signals you forget to connect. Okay, so these warnings are something for DDR interface from PS, and those warnings are fine, you can just ignore them. Okay, now once you have done this much, you should come back to the sources tab here, and here you will see led control.bd. okay, that is actually the block design, this one. Now you need to implement it. Now to implement, first step is you need to right click and say create HDL wrapper, and Vivada will create a Verilog file from this block design. Okay, so he creates this Verilog file and he automatically adds all the input output. For example, these LEDs, this DDR, fixed IO. All the signals are automatically added to this top module, and under that top module he actually instantiates this block design. Now later when you run implementation, he will fetch the Verilog code for this module, this processor system reset. This module is responsible for generating a power on reset signal to the processor as well as all your peripheral. He will fetch the Verilog for XC interconnect, he will fetch the Verilog for XC GPIO, and he will just implement all these peripherals on the PL part. This one, there is no special Verilog code because this is a fixed IP core, and he will connect them all together. Okay, so once you have done this much, you can just go ahead and click generate bitstream. You don't have to do constraint in this particular case because, as I said before, when I added GPIO, there itself I told I want this GPIO to control my LEDs. So he automatically knows what is the constraint for LED. Similarly, clock is coming from PS, not from Y9 pin. Okay, because of that you don't have to specify the pin for clock, and he also uh, knows the clock frequency is 100 megahertz, so you don't have to give frequency constraint also. Now wait until he generate bitstream. Okay, bitstream generation is completed. So usually we just go ahead and program the FPGA. That's what we used to do last time, but here what I'll do is I'll go to file and choose the option export and choose export hardware, and while doing that just check this option include bitstream. So what is going to happen is the address information of every peripheral in your block design will be saved in a text file, and that information will be exported, which can be used by the software development kit SDK. Okay, so first go and choose export hardware, and after that choose launch SDK. And wait until he completes the initialization, and you will see he's showing like importing hardware specification. Okay, so this screen you haven't seen before. This is something new. Okay, so previously you were not seeing this screen because you were doing independent software development, and at that time there were no custom hardware in the PL part. Okay, in this case that is not the case. You want to interface a custom hardware with the processor. So first you implement the hardware, then you export that information to software. And here you can see XC GPIO 0, and you will see this address here, base address, which is exactly the base address here. Okay, so this information is what got exported to SDK, and that information is coming through this file actually, system.hdf hardware definition file, and this is the file which got exported when you chose export hardware. So once this comes, you will go and again choose new application project and give some project name. Let's call it LED control. And one thing you will notice here, before we were always choosing Z hardware platform predefined, and this option you will choose when you don't have any peripheral in the PL part. If you have any peripheral in the PL part, you need to use that that detail when you write your software. Again, by default, he will give you this option here once you export your hardware to SDK and choose launch SDK. So again, basically this has the information about all the peripherals that you are going to implement in the PL part. So don't change this thing, and click next, and let's choose empty application, and you can choose finish. Okay, so let's go to the source and say new source file, and choose LED control.c and choose finish. Okay, so our aim is to write some data to the GPIO controller, and whatever data we are writing to this IP will be sent to the LED. Now, in order to write to this IP, we need to use its address. Okay, so the function, again, built-in function available to write to any peripheral is sil out. Okay, so this is the function. So you'll see a lot of functions are starting with sil because these are Xilinx functions. Now sil out comes in different varieties. There are sil out 8, sil out 16, sil out 32, depending upon whether you want to write 8-bit data, 16-bit data, or 32-bit data. Now we have only 8-bit LED, only 8 bits. So the best one is to choose sil out 8. And the function takes two parameters. One is the address where you want to write, and one is the data whichever you want to write. So the address is this one, and data we can write whatever data you want. Now if you wish, you can directly write the address like this and followed by some data. Let's write A5. Okay, now this is okay, but it's not a good coding practice. So we usually don't hard code the address here. Okay, instead of that, we will use some parameter. So what you'll do is you will include a special header file called XParameters.h. XParameters.h. This header file is again automatically created when you export your hardware from Vivado to SDK. Now if you want to see the content of this file or any file in SDK, you click it and press F3 on your keyboard, and this is that file, xparameters.h. And there you will see it lists the address of all the peripherals. Okay, not all these peripherals are in the PL part. A lot of them are in the PS part also, because from processor point of view, everything is like a memory map device. So here 20000, which is exactly this one. Okay, now instead of hard coding it, we will use that parameter declaration. Okay, hash define. So we'll use this parameter instead of directly hard coding it, because the advantage is later if you change the address or somehow you change your hardware design and the base address of the peripheral changed, that means you have to come back and change that address everywhere. But if you are directly using the parameter definition, okay, when you change the hardware there and when you export, this value will automatically get updated so that you don't have to change anything in your software. Okay, so this is the better idea. Always use the parameter instead of directly hard coding the address value. Okay, so int main, and okay, so I'll write only this much. Now this function sil out 8 or sil out 1632, they are all declared inside another header file called sil.io.h. Okay, Xilinx input output header file. That's where they are declared. So you need to add that one also here. Okay, so that's it. So our software development is done. Now we are ready to hit on hard. Okay, so the first step is to program the PL part. Okay, you need to program the PL with the bitstream. That you can either do from the Vivado, or you can do that also from SDK. Provided when you export, you check the option include bitstream, which we did. Okay, if that option is checked, if you come and click this option, program FPGA, that bit file will be visible here. Otherwise it will be empty. You can either browse and find it out, or you can come to Vivado and program from there. Anyway, first step is to program the PL part. Okay, so we are programming the FPGA. Make sure the blue LED is on. After that, same as we used to do for running the SDK. FPGA is programmed. Now you need to run the software actually. So that step is exactly same as what you used to do before. Go to run and choose run configuration. Double click on this one and choose standalone, local, and here this option is checked actually, program FPGA. That means each time you click run, he will program the FPGA. Maybe that's not necessary. We need to program FPGA only once and just rerun the software each time whenever I click run. So maybe we'll uncheck it and go to application and choose this option, which processor core, and make sure the ELF file is listed there and choose run and wait until this becomes 100%. When you run the code, you'll see whatever value you're running from SDK, same value is coming on the LED. Now you go ahead and just change this value to something else. Let's put maybe FF, save, and rerun again. Okay. And you'll see like all LEDs are on now because we entered FF. Okay. Now this is the one flexibility of software, you see, okay, or rather hardware software co-design. In if you are doing a pure hardware design, each time you want to change the LED value, maybe you have to change it in the Verilog code and go through the entire implementation again. But since the value shown by LED is controlled by the software, now you have more flexibility. You can decide what value should come on the LED by changing the values here. Okay, so that's it. So this is our first program which uses both hardware as well as software. See you in the next tutorial.